instead of the linear ODE with constant coefficients, we can also have analytical solution for the linear ODE with variable coefficient. And usually we solve this kind of higher order ODE using power series. There is a particular type called Euler Cauchy equations with variable coefficients can solve analytically, but it's much easier as compared to the polar series. So we will introduce this type of the equations in the lecture today. Okay, so Euler Cauchy equations. And what is Euler Cauchy equation? How it look like? So in general, variable coefficients, linear ODE, are difficult to solve analytically. We will use power series to solve it from analytical point of view. To address this problem analytically. Numerical, we will also usually use numerical solution to solve. Usually, we will use numerical solution. Okay, and one particular type for this variable coefficient linear ODE is called Euler Cauchy equations. And this is one type, one particular case of variable coefficients ODE. And then we will make a second order as a study case. So the Euler Cauchy equation look like this: double prime plus axy prime plus by equals to 0. So you can see the coefficients are not constant anymore. They are functions as function of x, the independent variable. And as the power of the x is the same as the order of the higher order of the y, the differential equations y. This is called Euler Cauchy equations. And usually the solution form look like x to the m. So it's a power of x. We will solve using similar ways as how we solve for the constant homogeneous ODEs. So that is y double prime will be equals to m times m minus 1 x to the m minus 2 power. Y prime will be equals to m minus 1 x to the, sorry, will be m times x to the m minus 1. Then you can put this y double prime and y prime back to your original equations. We can get m times m minus 1 x to the m's power plus a m x to the m plus b x to the m equals to 0. And you can see that at the left side, you all have this term x to the m. And you know that x to the m won't be 0. So we can cancel this x to the m out, which is m times m minus 1 plus a m plus b equals to 0. And this is the characteristic polynomials for Euler Cauchy equations. So this is characteristic poly for the Euler Cauchy equations. And in order to solve the two linear independent solution for Euler Cauchy equation, you need to solve this characteristic polynomial to get the root of m so that you can write the final either general solution or homogeneous solution for this particular case, right? So you get this m squared plus a minus 1 m plus b equals to 0, and you know m1, 2 will be solving the root of this equation, minus a minus 1 plus minus a minus 1 squared minus 4b divided by 2. And it really depends on what is the number of a minus 1 squared minus 4b. If that is real, then it will have two distinguished real root. Then you can directly write your final solution. If this one is a complex conjugate, then your root will look like cosine and sine combination form, or you will have some imaginary numbers in your solutions. Or if this will be equals to 0, then you need to solve another linear independent solutions using reduction of order. Okay, so we will introduce this three types of the root to see how the real solution look like. Okay, so for the real root, that is when you a minus 1 square minus 4b is greater than 0, then you will have basically two different real roots. So your final solution will look like a combination of the two independent solution. That will be C1 x to the m1 plus C2 x to the m2. And you know that this form can be rewritten as a hyperbolic function form, which combines cos and sine. Okay, you can write in that form in particular case, but we won't extend in this case. You can refer to the previous note regarding the constant coefficient. Okay. Second will be a complex conjugate root. And you know that is when your a minus 1 square minus 4b is smaller than 0. So that this root of this negative number will be a complex conjugate. And you can rewrite your m1, 2 will be some complex conjugate, where your alpha equals minus a minus 1 divided by 2, that is a real number. Beta will be an imaginary number because you are root of a negative number divided by 2. So that later on you can write again u by hx will be a linear combination of each independent root, which will be c1x to the m1, so alpha plus I beta, plus c2x to the lambda minus I beta. And you know that you can write this form as a sine or cosine function. Easy to imagine what is the physical plot. You can try to derive in that sense as well, but we won't extend in detail in this class. You can refer to the previous note in the constant coefficient. The third one will be the same root. So that is when basically you a minus 1 squared minus 4b is equals to 0. So that you have the same root m1, 2 will be equals to the same thing, which is minus a minus 1 divided by 2. So you only get one root, and in order to construct you complete solution of you homogeneous solution, you need a second linear independent solution, where we can use reduction of order to get the second solution. So in that sense, you know uy1 will be equals to x to the m1, which will be x to the minus a minus 1 divided by 2. So that is your single solution right now. Then we will use reduction of order to find the second linear independent solution. Okay. And our original form. So in order to use reduction of order, you know that you assume y2 will be equals to u, which is as function of x, y1, which is also as function of x, and then you will derive y2 double prime, y2 prime as function of u prime, y1 prime, so that you can replace your original equation, which our original equation will be y double prime plus a divided by x, y prime plus b over x prime, x second order y equals to 0. And you can write this as general form y double prime plus px y prime plus q x y equals to 0, where the px equals to a divided by x, the qx equals to b over x squared. Okay, and you can replace the y2 double prime or y2 prime and y2 with the function of u and y, u and y1, so that what you can get is the so we will replace y2 double prime y prime y2 with a function of u double prime u prime u y1 double prime y1 prime and y1. So some function of this, and to construct our final solution, what you can get is basically u double prime y1 plus u prime 2y1 prime plus py1 that is equals to 0. So after you replace this equations using u and y to fit into the original form, you can get this linear higher order ODE, which is higher order of u. And let u prime equals to z, u double prime will be equals to z prime, then we can get z prime y1 plus z 2y1 prime plus py1 that is equals to 0. And you can see that this become a separable equations, so that we can directly solve z as function of y1. Okay, so what we can do is go back to our z prime y1 plus z 2y1 prime plus py1 equals to 0. Then you can get the z prime divided by z will be equals to minus 2y1 prime plus py1 divided by y1. So that is a separable form, and you can just integrate both sides to get your final solutions, right? So what you can get is basically the zx will be equals to 1 over y1 squared e to the px dx. And you know uy1 is equals to x to the 1 minus a divided by 2. Upx is equals to a to divided by x. So you just replace this y1 and the px with its form of x. Then you can get the zx will be equals to, so 1 over x to the 1 minus a divided by 2 squared, which is e times e to the a over x dx. Then that is x to the a minus 1 times e to the negative a ln x. That is x to the a minus 1 times e to the, sorry, x to the minus a. So in the end, you get x to the minus 1 for your final solution for the zx. And you know that z is equals to u prime. So in order to solve you just integrate the z as function of x. So u will be the integral of x minus 1 dx, that is ln x. So your y2 will be y1 times u, which is ln x. And in the end, your solution will look like y homogeneous equals to c1y1 plus c2y2. And your y1 is x to the 1 minus a divided by 2. Your y2 will be x1 minus a divided by 2 times ln x. Okay, so for the Euler Cauchy equations, when you have repeated root, you basically the second root will be times ln x. That will be usually the second root. Okay, so for the Euler Cauchy equations, then if you have the same root, then usually the second solution or linear independent solution is to multiply ln x with that independent root, which is u by 1, so that you can get the complete solution set of your Euler Cauchy equations. Okay.